Assalamu alaikum wa rahmatullah. I hope that you are all fine. In the first lesson, we have reviewed all ideas about waves in general. Meanwhile, we are going to deal with sound waves in chapters 3 and 4, emission and reception of sound. Let's start with part 1 of this lesson. What should you know at the end of this chapter? Specify the nature of sound waves. Explain how a loudspeaker works. Explain how a microphone works. And indicate the range of audible sounds heard by the human ear. In this part, the first two objectives will be covered. Let's remember from the previous lesson the main differences between the mechanical and electromagnetic waves. Mechanical waves are disturbances that need a material medium to propagate in, but cannot propagate in vacuum, whereas electromagnetic waves are electric disturbances that can propagate in certain material mediums and in vacuum. Some examples about mechanical waves are sound waves, waves on the surface of water, or waves produced in a rope. Examples about electromagnetic waves: light waves, radar waves, TV waves, X-rays, gamma rays, and cell phone waves. The speed of mechanical waves is much less than the speed of light in vacuum or air, defined by c equals to 3 times 10 to the power 8 meter per second. On the other hand, the speed of an electromagnetic wave is equal to c in air and vacuum, and can be calculated using c divided by n in other mediums, where n is the index of the transparent medium. Mechanical waves are transversal or longitudinal, unlike electromagnetic waves, which can only be transversal. The wavelength of both waves can be calculated by lambda is equal to v divided by f, and their frequency is equal to 1 divided by the period. But in the case of an electromagnetic wave propagating in vacuum or air, v can be replaced by c. Let's start by studying the emission of sound. What is sound? Sound is a longitudinal mechanical wave produced by the vibration of an object in a material medium. Why it is longitudinal? Because the direction of vibration of the particles, marked by black points, is parallel to the direction of propagation of the wave. It is also a spherical wave. For example, waves emitted by a loudspeaker and waves emitted by the wings of a bee. In this chapter, we are going to study about the loudspeaker, memorize its main parts and its principle of functioning. What's inside the loudspeaker? The main parts of the loudspeaker are the magnet, the coil, and an elastic membrane. The main role of the loudspeaker is to convert an electrical signal when it is connected to a low-frequency generator into a mechanical sound vibration or simply a sound wave. Therefore, it is called an electroacoustic converter. Before explaining the principle of functioning of a loudspeaker, we should understand the electromagnetic force. When a current passes through the coil in the presence of a magnetic field or a magnet, an electromagnetic force is created. This force is capable of moving the coil. The direction of this movement is related to the direction of the current. What is the principle of functioning of a loudspeaker? When a sinusoidal electric current passes through the coil found between the poles of a magnet, it will be subjected to an electromagnetic force that causes the coil to vibrate according to the direction of the current. Being fixed to the coil, the membrane is subjected to vibrations, thus producing a sound of the same frequency as that of the current. Keep in mind that the loudspeaker is connected to an AC source, where the direction of the current varies every half cycle. That's why the motion of the coil is vibratory. It is moving forward and backward. For this reason, the loudspeaker will not function if it is connected to a direct current source, where the current has one direction, and thus the electromagnetic force will have also one direction. There is no forward and backward motion of the coil. That means no vibrations and no sound emitted. Propagation of sound waves. The sound propagates in air, like a longitudinal wave. The sound does not propagate in vacuum, it needs a material medium to propagate. The speed of sound depends on the medium of propagation, and since it is a mechanical wave, then it's faster in solids. Speed of sound in gases is less than that in liquids and less than that in solids. Here are some extra remarks about sound. The speed of sound in a homogeneous material medium is constant, and in gases the speed of sound increases with the temperature. The speed of sound in air is given by the relation V is equal to V0 radical 1 plus T divided by 273, where V is the speed of sound at a certain temperature T and V0 is the speed of sound at 0 degrees Celsius. Let's solve the following application. Far away in the night, an observer hears the sound of an explosion 5 seconds after seeing the flash of its light. Given the speed of light in air is c is equal to 3 times 10 to the power 8 meter per second. The speed of sound in air at 0 degrees Celsius is V0, which is equal to 331 meter per second, and at temperature T is V is equal to 340 meter per second. Part 1. Calculate the air temperature in this case, where V is equal to V0 radical 1 plus T divided by 273. In order to calculate the air temperature, we have to use this formula, square both sides, and then substitute with V and V0. Therefore, after calculation, we will find that T is approximately equal to 20 degrees Celsius. In part 2, we have to calculate the exact distance between the observer and the explosion. For the sound, the distance covered is D is equal to V times T1, then T1 is equal to D divided by V. For the light, the distance covered is C multiplied by T2, where T2 is equal to D divided by C. The difference in time is delta T is equal to T1 minus T2, which is equal to D divided by V minus D divided by C, which is equal to D into 1 over V minus 1 over C. After substitution and calculation, we will find that the distance is approximately equal to 1,700 meters. One of the most common daily life examples about speed of sound is the sound barrier, جدار الصوت. How does it happen? An airplane usually produces a sound that radiates in all directions. First, we have to know that if this airplane is stationary or not moving, then the corresponding wavefronts will be equidistant. But what if the speed of this airplane is very high? What happens to the wavefronts? Here we have to distinguish between 3 cases. First, if the speed of the plane approaches but less than the speed of sound, then it is said to be a subsonic flow. That means the disturbances propagate at the speed of sound, which is greater than that of the plane. In this case, the sound pressure or waves pile up on each other, or they get crowded, causing air particles to be compressed. In other words, the wavefronts get closer to each other. These disturbances dissipate in the atmosphere. What if the plane flies at a speed which is equal to that of the sound? In this case, the sound wavefronts accumulate in front of the plane, where they become confounded to form a wave called a shock wave or a sound barrier. In the third case, the plane flies with a speed greater than that of the sound, called a supersonic flow. as if now the air particles cannot move away from the plane. Then the wave fronts accumulate and superpose to form a cone whose vertex is at the nose of the plane. The air particles here accumulate to form something like a cloud that can be seen in this video. The sonic boom is a powerful explosion which can be destructive for unequipped planes. I hope that you were interested with the information that we have studied in this video. It's the end of part 1. Study well, please.